First, I want to thank Siyavash and Shyftlabs and Shobit, who is a visionary, and we really enjoyed working with them. The whole process took a few months to go through all the rigorous testing, and along the way, they actually helped us. They tipped us, okay, here we have a bottleneck, what's happening? So at every step, we went back, tried to find out what is holding the high throughput architecture. And after rounds of problem solving and engineering, I think we achieved something that is not easily replicable. And everything is also designed as infrastructure, as a code, so it's replicable as many times you want. And actually, Shift also pushed us to replicate this on other cloud, on GCP, which I will talk about. But now, I want to shift the gears and talk about the underlying, what's happening inside the moorcheh and how we came up with the idea. Okay, yeah. And I was thinking on what makes us different, and I realized that my background was data science. So I've been working as a lead data scientist and scientific programmer since 2012. And my approach was not the same as the database engineers. So database engineers came in, looked at the vector database, and they saw another classic database problem. So they applied exactly the same tools to vector database. So what happens is that you take these text or elements, you pass them through neural networks, and you end up with these what we call embeddings, which is the weight of the last layer of neurons. And they are, what we call them vector, is actually the output of those neurons that have been trained to understand the meaning behind words, sentences, paragraphs, images, right? And the model that they used was to solve a very immediate challenge. Because if you take a text that is few paragraphs or few pages, it's a very small amount of data, so maybe 1 kilobyte or less. But when you transform it into vectors, now you are dealing with each vector turns into 1,000 or 2,000 float numbers. So your the amount of data that you have to work with suddenly explodes 25x or more. And this is not good. We usually want to compress things, but now imagine all the libraries, all the knowledge of on the internet has to be multiplied by 25. So that's a panic mode for engineers. And what they did was to come up with classic methods, like having more cache things, put things in the storage, bring them back on the RAM, create these tree structures. But we took a step back and thought, what is the problem here? It is the entire RAG has to be looked at as a holistic problem. We are ultimately designing optimized context for the AI LLMs to do their job or duty properly. So if you look at the problem this way, from a point of view of data scientist or AI engineer, you see that, okay, I don't want to get involved in all the engineering systems. So what we did is went back to the most fundamental problem in the most fundamental theory in entire, so let me go back, in entire IT, so information technology, mostly comes from information theory, or Shannon's theory of information. So you go to basics, you have a method of compression, you can prove mathematically this is the most efficient, and you have a limited channel and you want to retrieve information. And that's all it is. But now, now we see the symptoms of what other vector databases were trying to do. So they started to see that there's a lot of RAM requirement. Now there's a shortage of RAM. Now the expense of RAM is going up. You cannot really scale without a very high price tag. And they started to separate the storage. That's actually one of the good solutions, but it's not the holistic solution. And they have different methods of quantization with different variable levels of losing the accuracy. So I believe that the entire HNSW-AN, although it's a very amazing algorithm, so it creates a tree structure, it's a order of log n operation, which is very fast. But these challenges are making the entire problem more difficult to scale. First of all, we are dealing with nearest neighbor, which is always an approximation. You have to keep updating your tree structure, which is a very painful process. I'll talk about more. You're dealing still with float vectors, and we're using cosine similarity. Actually, cosine similarities are used to train the embedding models, so the whole system feeds into each other somehow. But now, as a data scientist and as someone who wants to build a perfect AI workflow, I'm not okay with approximation results. So if I have a data set, if I have a haystack and there's a needle, and I need to find that needle, I want that needle to be found. I don't want to be around the haystack around the needle. So in my approach was that we should have the exact scanning and the exact vector search. But people didn't do that. All the available vector databases use the same stack. They have approximations. And now you see the trend in the industry is actually symptoms of those effects. So people now are trying to merge the keyword search with the semantic search. No, semantic search is supposed to be the highest, most advanced method of search now. Now people are going back. They're using 30% keyword search with 70% semantic. Or there is the whole industry built around re-rankers. It's like a very expensive, like 2-3 cents per 1,000 tokens or so. And without that, you don't have the production quality. You can opt out, but your system would suffer in accuracy. And then another symptom that I see was recently ChromaDB open sourced some of their code, and they said, okay, we have agentic search. And by that, they meant that just give the text to an LLM agent, page by page, and let it go search through it. Which I think is like just using a very advanced technology to do the search technology that we have been doing for a very long time. Okay, so these are symptoms, but they don't cure the underlying problem. Now, and I told you about the tree structure behind the behind the approximate nearest neighbor, HNSW, or clustering methods. And as soon as 10% of your database changes, you have to go and reindex or accept that your quality of search is going down. And sometimes when you have large data sets, new data comes in, people upload new data, take out data. You have to wait for the whole system to reindex, to rebuild itself, up to 6 hours sometimes during the night, if you don't know, but the cluster is running. And some of the architectures, when the database is restructuring, you cannot query it, so it's out of use. Who likes that? And so that's what we, like me as a engineer, like as a scientist, I didn't like all of this. And fundamentally, there is a trade-off that everyone accepted, is that you have lots of queries, and you should accept that if you want to increase your throughput, you compromise accuracy. And so as your throughput goes up, your accuracy would go down. And this was the fundamental trade-off that moorcheh is breaking, basically. What we are saying is that let's replace the entire stack, not just a better caching system, not just separation of storage, not just a smarter tree structure, but the whole thing. And again, we go to the fundamental, the information theory, Shannon. Basically, you have we take the vectors, which is the output of neurons, as random signal, and we treat them with the tools of signal processing. So we say, okay, this is coming in, I'm compressing it the same way that I would compress a sound wave or a JPEG or MPEG, the same method. And I have an output channel. Usually we compress it 32 times to become a binary. And once it's a binary, I know how much information I lost. And basically 6,000 bytes goes to 192 bytes. The second part was that, okay, now I only need these binaries. I throw away the vectors, the float numbers, and I take these binaries as indexes. And now, because I'm not a database engineer, I mount it on a very well-optimized database. Okay. So we tried different things, like on AWS, we go with DynamoDB, which I love. It's super optimized. It's a technology has been improved for 30 years, right? And I just put my binaries there and I cache them whenever I want to do the retrieval processing. And then the retrieval itself has two steps. First, we do the what is called as a Hamming distance. And this is optimized because it's a CPU level XOR operation, and we use ROST. We use some techniques. We did a lot of sharding to go to avoid bottleneck of retrieval from database. Then we use ROST and optimize it for architectures on CPU. That's where our collaboration with Intel came through, because if you want to do it on-prem, it's already optimized for CPU. It can be optimized for ARM architecture as well. And the best thing was that when we moved it to Lambda functions, we achieved distance metric of 10,000 vectors of dimension 1,000 each. That's like 10 million operations in 6 milliseconds. And once we achieved that, I said, okay, we're in the safe zone. Okay. And then the second step of the retrieval is to bring back the lost information. So it's information theoretic score goes back to my research at my PhD when I was working on atmospheric science and verification of rain and snow forecast. And I really like it because it's an information, it's a score that shows you systematic similarity and not a random overlap between two signals. And relying on systematic similarity, and it can be optimized, so it has a lot of use down the line when you want to measure the relevance of your answers to LLM and even put guardrails. Okay. Now, with that, we achieved, as I said, obviously memory compression. We don't lose accuracy. This is like our red line. We did a lot of Mayer benchmarks. Compared to cosine similarity, even though we're compressing so much, we're not losing the retrieval accuracy. And we have a well-functioning proof of concept so far, because we need to still solve some of the engineering parts, which connects to what Siyavash was telling. And that's, so now that I don't need to reindex things, I can ask Siyavash or another company, let's upload all your files, bring it on. And then when they did the pressure testing, the entire architecture was running on their own private cloud. We didn't have access to that. And we didn't even know what they're doing with the pressure testing of moorcheh. And 10,000 vectors, 1 dimension, 6 millisecond. And from there, it goes higher in time. And that baseline became our standard to make everything much faster. And then another advantage is that as soon as they upload the file, it's available for querying, or at the same time. There's no delay. Or deleted, if you delete a file, it's deleted immediately. It's like a transactional. And over time, we realized that this ITS relevance score acts as a built-in re-ranker. So every response that comes from moorcheh is already ranked. And you can actually put a threshold and say, I want the top 10, top 20, but automatically remove anything that is below this threshold for me. That was a step that most people still do it manually. They submit it to the re-ranker and bring back, remove the irrelevant context. Yeah, so our target was to approach the entire end-to-end RAG. It's not just about the vectors. It's not just about one part of the equation. And with that, once you have the built-in re-ranker and you have the built-in connection between the LLM, the storage, and the local tiny workers, you bring down the entire end-to-end timing. So what Siyavash was showing you was not just the retrieval. Some of the graphs was showing you the whole, from the time you submit the query to getting the answer. And then we reached actually the bottleneck on AWS for the quota of how much you can call the backend embedding model, like cohere method. Cohere embedding was used in that case. And so the bottleneck that Siyavash showed, he was showing if you have 20, 50 people submitting queries all at the same time, but those are questions, those are texts that have to be embedded, then turned into binaries, and then put into the search and get the answer. And then we didn't have bottleneck on the moorcheh itself, but we hit the quota on Cohere on AWS Bedrock. So we have no clusters, no idle cost, and that's one of the things I really love from being a cloud architect as well, is that if I'm not using it, I don't want anything to be running. I don't want background services, I don't want background clusters, I don't want to manage clusters. So you are not managing any cluster. Everything is performed with microservices, both on AWS architecture and on GCP architecture, which it takes us to, so these are moorcheh, okay, this is the load that moorcheh can handle, concurrent number of queries, and compared to Qdrant, Elasticsearch, and Milvus. By the way, our white paper is published on arXiv. I can share the link with you. There's a thorough study that we did ourselves on both timing, latency, accuracy, and throughput. And overall, if you add up the cost of clusters, cost of ingestion, cost of running and managing the databases, cost of re-rankers and cost of all the effort that has to go into building a fully optimized rack system, which takes 6 to 8 months of intense engineering to get it all working and all give you correct answer, reliable accuracy. That's where moorcheh really pays off, because it's replicable architecture, and it saves a lot of cost on both clouds. Now, after we worked with Siyavash, they kept giving us more requirements. One of the things was that, can you guys upload a file that is 10 megabyte? And then we restructured the whole thing. Now we can ingest up to 5 gigabyte. A single file is up to 5 gigabyte. No problem, bring it. And now we ingest natively audio file, video files, and tables, charts, scanned documents, everything. And so this is the final chart. You can be a data scientist or AI engineer and not worry about what's happening on the cloud, and just work on your product. Yeah, that's it. Thank you very much. Now, if you have questions from me and Siyavash together, we'll be happy to answer.